Okay, so continuing with the same. So, for a room of volume V, total reverberant field energy will be epsilon into capital V for the whole room. So, now we can apply the conservation of energy for the whole room. So, what is the energy that would be actually entering into the reverberant field is epsilon V, right, and after first reflection, after first. So, we got to define something, right. So, energy entering into the reverberant field must be equals to the energy absorbed in all surfaces, because how will the energy enters into the reverberant field after first reflection, because till the first reflection it is all direct sound, till the first reflection it is all direct sound, right. After the first reflection it is entering into the reverberant field, because reverberant field consists of all sound after first, second, third infinite reflections. So, after first reflection it enters the reverberant field, and where does it go? If it was not lost somewhere, the diffused field would have gone on increasing all the time, but that does not happen. So, there must be somewhere it must be getting lost, that is actually get lost at the surfaces of the boundary surfaces of the enclosure through absorption, through absorption. So, that is what we are saying. So, energy absorbed in all surfaces. How much energy is incident upon the surface, that I have found an expression. How much will be absorbed, I must find out now or define in some manner. So, we define a term called absorption coefficient. Okay, I will come back to this expression later on. Perhaps I have got an expression for energy absorption. Absorption coefficient is denoted by alpha, is the ratio of energy absorbed to energy incident. For number of surfaces, average absorption coefficient we find out, weighted average, area weighted average. So, how much is the absorption coefficient of a window? Energy incident, energy absorbed divided by energy incident is equals to 1. Open window it will be 1, because everything will go away, right. So, energy absorption is defined in this manner here, right, in the context of sound in enclosure. Unlike the absorptivity when we talked of heat, right, we are talking of opaque surface. So, it will have three component alpha plus T plus R, fraction of energy absorbed, fraction of energy transmitted, fraction of energy reflected, right. Here, since we are interested in an enclosure, how much energy is coming back or how much is getting absorbed. So, we are defining it in a slightly different manner, right, for those material, for the wall or ceiling material. But if we look at transmission, then these three issues also comes into picture. We will see that later on sometime. Okay. So, at the moment ratio of energy absorbed to energy incident for any wall or any surface, I call it absorption coefficient. If there are large number of surfaces, because in an enclosure I will have at least 4 plus 2 6 surfaces, and their areas, 2 of them might be same, another 2 might be same, another 2 might be same, but it is not necessarily all are same, and their absorption may be different. For example, ceiling and floor absorptions could be different, walls may have a different absorptions. So, in that case we talk in terms of average absorption coefficient, which is defined like this, alpha bar. So, alpha is equals to energy absorbed divided by energy incident, and alpha bar is surface area multiplied by alpha I divided by sigma. So, this is average absorption, that means nothing but weighted average, surface area weighted average, right, multiplied by corresponding alpha. So, I 1 2 3 for all surfaces, alpha bar is average absorption coefficient, alpha bar is average absorption coefficient, right. So, alpha bar is average. So, now then let me go back to the previous slide again. Alpha bar I am calling as average absorption coefficient, right, and average absorption coefficient. So, if you recollect, what we said was energy density into energy density into remember we talked of the energy which is incident upon into the volume into the volume, into the volume into what was it? What was it? Energy incident. Okay, let's go back and recollect. So this is energy density of the reverberant field multiplied by C divided into S divided by 4. That's what, So let me just go back still further to remember. So this is the power received on a surface S. So epsilon r is the energy density of the reverberant field, C S by 4 is the energy received onto S surface area. Supposing this S is the whole room surface area, then this is the energy received on all surface area. How much of it will be absorbed? Multiplied by alpha bar. Multiplied by alpha bar. That will be the energy absorbed in unit time. That is the energy absorbed in unit time, right? Am I right? Is the incident power, because we are talking of power. So this is the energy absorbed in unit time in all the surfaces. Alpha bar I am defining for all the surfaces. So S is the S alpha bar, that is what it is. So this is the energy absorbed in all the surfaces. Now this is how the sound is lost from the reverberant field, from all surfaces. So how much is coming into the reverberant field? Epsilon V, total V, volume of the room is V, and we are calling it epsilon R, which is reverberant field has got uniform density, right? Now only after first reflection the energy is entering the reverberant field. So in the energy lost in after first reflection will be this into alpha bar, because this is the energy, total energy contained in the room, multiplied by alpha bar is what will be lost in reflection. So epsilon r V into 1 minus alpha bar, that is the energy entering into the reverberant field, and that I might equate to this. That I might equate to, because energy absorbed must be equals to energy entering into the field. Energy entering into the field is if the volume of the room is V, epsilon r into V, because it is uniform throughout into volume, that's the total energy. 1 minus alpha bar is the energy entering after first reflection, and that must be absorbed in all the surfaces. So I can get an expression equating these two, which I am doing later on. So I have defined. So you see, epsilon V in case of steady field exists, energy entering into the reverberant field must be equals to the energy absorbed in all surfaces. Absorbed energy per unit time on the surface S is given by alpha bar, epsilon r C S alpha bar by 4. For all internal surface area of the room S, this is in terms of S alpha bar by 4 is the energy lost from reverberant field. That is what just I was mentioning. So energy lost from the reverberant field will be given by this, and that must be equals to energy entering into the field. So energy entering into the field is reverberant field is, okay, sorry, I made a mistake. This is not epsilon V, this will not be epsilon V. Epsilon V will into 1 minus alpha would be at any point of time, but actual power comes from the W source. After first reflection I am talking of, W is the power of the source, W is the power of the source, because I said I have a steady source. So W into 1 minus alpha bar is the energy entering into the field after first reflection, not epsilon V. Epsilon V will be at any time, which will be a function of time. We will look into that later on. So that way we see that this is how we define absorption. So energy balance, therefore one can write, energy balance, therefore one can write is W into 1 minus alpha bar is equals to this. Energy balance from the conservation of energy, one can write this. Now this gives me an idea actually to find out IR or reverberant field intensity and then decibel level, because E was epsilon density was related to IR. Remember, this is epsilon r, and epsilon r was simply IR divided by, right, IR divided by C. That is how we talked about. So this is, I put it, therefore I can put here IR by C. So it will be simply IR by C4 C S alpha bar. So the C will cancel out, I will be left with IR S alpha bar by W, right. This is what I think is done in the next slide. So epsilon r is equals to, I get an expression for epsilon r by simply doing a little bit of algebra out of this. epsilon r is equals to W this 4 W into this divided by C S alpha bar, that is what is been written, C S alpha bar, and this I am writing as I R by C, this I am writing as I R by C. So, this is nothing but I R by C, and total energy density will be written as direct as well as reverberant field, and intensity of direct and intensity of reverberant field, and this is I D is the direct, and I R was C into epsilon r, and I am just putting it epsilon r here. So, I will get the expression for total one like this, I R is equals to W, because C will cancel out. You know, that is what I was saying, W into 1 minus alpha bar was equals to epsilon r C S alpha bar by 4. Was it, is it right? That is what I did, right? That is what the equation was. Now, if I replace this by epsilon by I R by C, then I get W by 1 alpha bar must be equals to I R C cancel out S alpha bar divided by 4. So, this becomes I R is equals to 4 into W into 1 minus alpha bar divided by S alpha bar, right, S alpha bar. Okay, so, that is the reverberant field density. Total field density will be given by this plus the direct field at any point. At any point, if I am interested, I will find direct, which is a function of the distance r, and this is independent of the distance, because it is uniform throughout the room. It is uniform throughout the room. So, total will be given by this sum. Total will be given by this sum, epsilon density, epsilon I D I R. So, this is how it is. So, total will be direct as well as this. So, we will come to that in a moment. Now, out of all this, if you look at it, out of all this, if you look at it, this is the property of the walls. This is area of the wall. So, this component is actually property of the room, property of the enclosure, wall properties and the surface. So, we call a term called room constant, whereas this is the source, steady source that I have. So, I call something called room constant, and room constant is defined like this, S alpha bar divided by 1 minus alpha bar. More the room constant, less will be the reverberant field intensity, less will be the reverberant field intensity, right. So, that is right. So, I T therefore can be written as 4 W by R, because this I will replace as 4 W by R, and I T was what? Total was I direct plus reverberant. Direct is W q by 4 pi r square, remember that earlier we talked of direct field. So, total I T will be given by this, and if I want to find out the total level, then I can now divide by I reference and take 10 log of that, and that will give me the decibel level due to direct and diffuse field together. If it is only diffuse field, then simply take 10 log 4 W by R divided by I ref, that will be simply level due to reverberant field, because this was the intensity, this divided by reference intensity, but then in a room it will be total together. Any point you will have total only, you can neglect one or the other. So, therefore, I log I T by I reference is given by this, and which I can separate out. W is there in both of them. So, I can take out 10 log W by I ref plus 10 log Q by 4 pi r square plus 4 r, and I ref we know is equals to W ref, and therefore, this is nothing but L W. So, finally, this is my equation SPL, because we said intensity and power level is more or less same, assuming rho C is similar, rho C standard rho C and rho C actual are not very different. So, this is equals to power level plus 10 log 4 by this is the expression. So, these rooms are called semi reverberant room, because you have some portion direct as well as some reverberant field existing there. So, we call it semi reverberant field. Power level plus this right. So, this is what it is. So, I'll follow it up, but let me go to the diagram that I had. I'll go to the same diagram. I'll go back to the same diagram that I had. Remember this diagram. So, level I want to find out any point. It will be of direct as well as reverberant field, and this will be given as PWL plus 10 log 4 by r plus q by 4 pi r square. So, this is the level at any point, level SPL you call it, or LI, LP, whatever you call it, power level. So, it is given by this. So, at any point I can find out this. Now, you look at this, at this point, somewhere around this point, direct sound tend to be lower than the reverberant sound, right, because it is inversely proportional to R. So, there is a point where my direct field or direct intensity and reverberant field intensity are same, that we call as room radius. Room radius. So, room radius is that point where I have got room radius is that point where I have direct field and reverberant field are same, direct field and reverberant field are same, right. So, this is how I am defining. Let us come to that. So, this is how I am defining, right. So, room radius. Room radius is the distance from the source at which direct and reverberant field intensities are same, and when they can be same, q by 4 pi r square must be equals to 4 by r, because w q by 4 pi r square was equals So, it will be something like this. It is simply written like this, q by 4 by r. So, room radius is given by q r divided by 16 pi, right. Now, if your r is large, means lot of absorption, because r is what? S alpha bar by 1 minus alpha bar. So, for large value of r, this value will be, depending on for higher value of alpha bar, for alpha bar can vary from 0 to 1 only. So, for higher value of alpha bar, r value will be, room constant is it will absorb large quantity, it will absorb high, right, because this will be smaller and this will be larger. Let us say it is 0.9, so this is 0.1, so it is high, which means that your room radius is, for higher absorption, room radius is higher, and when absorption is very small, let us say 0.05 or something like that, reverberant field will be more and r is very small. Now, normal rooms, enclosure like this, classrooms, etc., they are semi reverberant field. You have some direct sound and some reverberant sound, reflected sound, some reverberant sound, right. A perfect reverberation room where testing is done will have very little absorption values. Alpha bar will be very small, alpha bar will be very small. So, that most of it is r, small r, this is small, then this is small, most of the room is then you get diffused field, reverberant field. You want to do experiments is done on reverberant field, like reverberation room. This is semi reverberant, these are called semi reverberant, semi reverberant or semi reverberation room, sort of semi reverberant field. You will have both direct as well as reverberant in most of the classrooms, auditorium, but there are rooms where experiments are conducted. You want to find out the absorption coefficient, this is done in reverberation room. If you want to find out the characteristics of a machine, its directivity, then you do it in an anechoic chamber, anechoic chamber. Anechoic chamber is where you will have all direct sound, absorption will be very little, because you have to isolate the room from surrounding, no noise should come from anywhere. So, there is special room, actually foundation is isolated, everything is isolated, no vibration coming from anywhere, total insulation, and anechoic chamber is where you will find out the machine characteristics, anechoic chamber. I am not discussing them in detail. Anechoic room, no echo, and reverberation room, they are just the opposite, all echoes, all reflection, here no. So, this is where you test machines for their directivity, how much noise do they generate, because you want to find out the noise generated by the machine, not the, but you can't do it in open field because there will be other kind of disturbances. So, that is why this kind of rooms are okay. Real rooms are semi reverberant, right. Real rooms are semi reverberant, okay. Real rooms are semi reverberant, and that is the diagram. Direct sound reduces with distance, reverberant field remains constant. So, this is your diffuse field and actual curve becomes like that, that is what we have seen, and this is your sum, this is your room radius. Just quickly we will define certain things. Now, it is important, two things are important. So, if I want to have noise control within a room and noise is generated in the room itself, then I will go close to an echoic behavior or less reverberation I would like to have. And if I want the sound to persist or it is a good sound, then I would like that it remains for longer period of time kind of. So, depending upon the type of sound that is generated or a type of room, the functional use of the room, I might like that sound persists for or sound remains, reverberation remains or reverberant field remains. So, we talk in terms of rate of loss of energy in the diffuse field, right. We talk in terms of, because I said reverberation is a phenomena of persistence of sound in the room even after you have put off the source, right. So, this is important, how much is the rate of loss. So, once I have put it off, recollect that it will be steady, then it will go like this, right. It will build up like this, steady, and then it will go like this, it will go like this, right. So, this persistence is important for me, this part of the curve, this is time versus level, dB values. So, this is important for me. Some cases I would like it to be there, some cases I do not like it at all. So, but it is important. So, this rate of loss of energy from this diffused field, because direct field I have cut off, I have put off the direct field. So, it is the diffused and reverberant field that will remain. So, rate of loss of this sound from a diffused field is an important issue, and this rate is depending upon the boundary, absorption in the boundary. First one to go away, direct sound goes away, then the first reflection will stop. The one which started long back will still continue to come, nth reflection will still continue to come. So, that is why this sort of a curvature. So, we would like to study how it is. So, the energy is lost at the boundary of the surface from the diffused field, boundary of the surface absorbed at the boundary. So, epsilon b is the total energy in the room. So, rate of change of this energy, because it is negative, because it is reducing down, what was this? This was incident upon all the surfaces S alpha bar is absorbed, this is the energy density C by 4, this is the intensity, right, multiplied by this is. So, this is the total reverberant field energy, epsilon r into V. Epsilon r into V is the total, because energy density multiplied by total volume of the room. Its rate of change dt is equals to intensity, this is the power per unit time, power. So, energy per unit time. So, rate of change of power must be equals to it. So, we are only talking of the diffused field. This is the intensity of the diffused field multiplied by S alpha bar, that is lost at the surface. So, rate of loss at the surface is given by this. So, therefore, if I extend this, integrate it, V I can take out to this side, and d epsilon by epsilon coming in here, this is a minus sign, C S alpha bar by 4 V and dt. So, this would be 0 to some value, whatever value I want, and it was the initial to some final value. Initial was this value, then there is some value final value I can find out. And time, of course, it was function of time. So, I can find out the rate of decay of the sound, and as you can see, this will be ln epsilon 1 by epsilon 2, because there is a minus sign. So, it is ln epsilon 2 minus ln epsilon 1 minus epsilon 2, because this is epsilon 1, let us say, and this is epsilon 2, epsilon epsilon, I mean that is going from initial to the final, and this then would be written as initial at any time epsilon t, epsilon m is equals to e to the power, if I integrate this, okay, let me just do it for you fully, let us do it actually completely, let me do it. So, this will be ln epsilon going from epsilon initially that was there to some epsilon t, there is a minus sign will come here, and this will be C S alpha bar by 4 V t, right. So, this I can do one thing, I can put the minus sign here, this is one way of doing, and then it will be simply epsilon ln e to the epsilon it will be simply what epsilon epsilon t ln like this will be e to the power, okay, let me put this on later on. So, it is epsilon is equals to epsilon going from epsilon starting to epsilon at time t is equals to e to the power minus 4 C S alpha bar by 4 V t. So, that is what it would be. So, so epsilon t minus or epsilon this can be written, how do I write ln epsilon by, so epsilon t by epsilon m, ln epsilon t by epsilon m will be equals to minus C S alpha bar by 4 V t, that is what after integration is. So, if I put e to the power all this, it will be epsilon t by epsilon m. So, epsilon t can be written as epsilon m multiplied by epsilon t can be written as epsilon m multiplied by e to the power minus C S alpha bar by, that is how it would that is how it is. So, that is what we have done, right, that is what one can write, that is what one can write, and this is what is written. So, you see at any point of time the energy density you can find out from the, now I just defined the last point for this this time. The last point is, so this is the relationship. So, epsilon at any time t is epsilon at starting just after you have put off the switch, e to the power all this term is a function of minus t, e to the power minus t, that is why the curve is something like this. Now, I can define a time, it is very difficult to actually fix time because it is related to starting point also. So, epsilon t by epsilon m, I can define this ratio, the time required to reduce this from its original value to some value. So, what we define? We define in terms of that when this ratio become 10 to the power, this is bigger, right, this is smaller, 10 to the, so this should be equals to 10 to the power minus 6. That means, when the sound reduces to 1/millionth of its original energy density value, that time I can consider as a standard time showing the characteristics of the room, because this is related to the room S alpha bar V, this is related to the room. So, how good the room is in persisting the sound or keeping the sound or dissipating the sound, that I can find out if I know epsilon t by epsilon m, some ratio, it is taken as 10 to the power minus 6, right. So, the time required for sound to reduce for its original value to 1/millionth of its original value is called as reverberation time, right. We will talk about this more in the next class.